A lot of interesting stuff happens in the hallway. It happens, you get to walk out of a session and there's a collective experience that you just went through. And so there will be a hallway conversation that springs up discussing the material.
All right. Hello, everyone. I'm Ben Sachs. Welcome to Back to Basics Initialization. My company, Sachs & Associates, offers training in C and C++ for companies all over the world. So if you're interested, here's our contact information. There's a lot to get to here, so let's go ahead and dive in. As you may very well be aware, initialization in C++ can be quite complex. There are a number of different forms of initialization in the language, different terms that get thrown around. And just as a fairly straightforward example of how this kind of confusion can manifest, depending on what type T is here, those two statements might invoke the same constructor, or they might invoke different constructors. We're going to talk about when it is one case versus the other and how you can tell the difference. I'm hoping that this will help you keep the initialization rules a little bit clearer in your mind and help you understand why the initialization rules are the way that they are. So we're going to delve a little bit into the history of initialization in C and C++. I'm going to talk a bit about the rules that we inherited from C. Look at the new rules that were added in the early versions of C++, and then talk about some of the ways that we tried to improve on those rules in modern C++, the benefits we got, some of the lingering points of confusion that still remain. So in C, we had scalars and aggregates. So scalars are simple values. They don't have any internal structure, things like integers and characters. Aggregates are things that do have some kind of internal structure. We think of them as being made up of smaller pieces, although a struct that has one field in it or an array of a single element, those are still considered to be aggregates in C. Unions aren't technically aggregates in C. They can be in C++, but they follow a lot of the same rules regardless. So when we're talking about scalar values, the typical way to initialize something like that is like this. Then equals followed by an initializer value. In C++, we would call this copy initialization. C doesn't really label the different forms of initialization the way that C++ does. It just kind of says, here are the ways you can initialize things. But in C++, we have enough rules that we need different terms for things. So for scalar values, that's how we initialize them. For aggregates, we can perform what we call aggregate initialization, where the initializer is a brace-enclosed list, and each element in the brace-enclosed list is taken as the initializer for the next element in the aggregate, whether that's the next field in a structure or the next element in an array. We can also initialize unions this way, though it has to be a single value in the braces that goes with the union's first declared member. When we're talking about structures or unions, we can also copy initialize those things from a compatible type, usually an object of the same type. So here, after creating a single object of type widget using aggregate initialization, I can then create a second one, U2, by copying from that existing widget. This is something that only applies to structures and unions. Neither C nor C++ lets us copy initialize an array. Now, I've talked about objects with explicit initializers. If an object doesn't have an explicit initializer, how it behaves depends on where and how it's declared. So if the object has, as we say, static or thread storage duration, which means it's declared static, thread local, or at namespace scope, it gets 0 initialized. That is, initialized as if the initializer was a 0, or a set of zeros in the case of an aggregate. If we're talking about pointers, pointers are initialized to null, whether or not 0 is the literal way that null is represented on your platform. There are some that do things a little differently. Otherwise, like if we're talking about an object that's just local to a function, the object will be left uninitialized in C. It'll have what we call an indeterminate value, which usually means that if we try to read from that value, we'll get undefined behavior. Not necessarily, but generally. Back to aggregate initialization for a moment, if the brace enclosed list stops before it's covered all of the members of the type or the array, all of the remaining fields are 0 initialized. And that pretty well covers the initialization rules that we got from C. You can kind of see why they didn't feel the need to invent specific terms for individual kinds of initialization. C++ introduced a number of new initialization rules because we have class types and constructors, and also because that introduced some complexity having to do with the notion of an object's lifetime. In C++, an object, its lifetime begins once it's been initialized. C doesn't really have the same distinction between when the storage for an object exists versus when the object itself starts living in that space that's been set aside for it. So, as an example, here is a class demoster. A demoster contains 2 fields, a size t and a pointer to character. This is just one of several potential ways that you could represent a string, and the C++ string class is significantly more complex than what I'm going to be showing you here, but this is just for illustration purposes. So this demoster type stores its contents in a dynamically allocated array. So the stored length here, if the string is hello, the stored length might be 5, and actual stir is pointing to a dynamically allocated array of characters that is null terminated. Again, this is just one possible way of representing a string, but looking at this, we can come to a conclusion that there's something that should generally be true about demoster objects. That is, that the stored length should always be 1 less than the size, the dimension, of the array to which actual stir points. This is something that we call a class invariant, and it's one of the main reasons that C++ needed new initialization rules, because if we were to try and work with demoster using the aggregate initialization rules from C, someone could create a demoster like this. If demoster supported aggregate initialization, someone could go ahead and create one that has a length of 5, but says it's the null pointer for the array, in which case that invariant, that thing that we always want to be true, would not hold for that demoster ds here. And that the root of the problem being that when we're talking about aggregate initialization, it's really the user of the type that has control over how the object gets initialized, what values are chosen. So it would be up to the user to know what things are supposed to be true about a demoster and enforce those themselves. The the author of the class can't really impose any restrictions in that situation. With constructors, demoster can impose those kinds of restrictions. The author of the class decides what constructors are going to do, and they can write those constructors so that the class invariance will always hold. And so that leads to the notion that if a class has user-defined constructors in C++, it doesn't count as an aggregate, and therefore it doesn't support aggregate initialization. More specifically, in C++03, the definition of an aggregate was something that has no user-declared constructors, no private or protected non-static data members. So all of the traditional data members would be public, no base classes, and no virtual functions. Now, more recent versions of the language have revised those restrictions a little bit. So now, in C++20, and there have been changes in between C++03 and C++20, but just to summarize, it's now no user-declared or inherited constructors, because aggregates are now allowed to have public base classes. They can't have private or protected base classes, and those base classes can't be virtual, but aggregates with public base classes are allowed as long as they will have all public non-static data members as a result. So suppose that our demoster class has the following operations that it supports. So it has a default constructor, a couple of constructors that are meant to operate in terms of arrays of characters, and a copy constructor, as well as a copy assignment operator and a destructor. When we initialize an object of type demoster with parentheses, that's what we call direct initialization. So these are both examples of direct initialization. Each one invokes a different constructor there. Now, direct initialization can also take place in other places, like in a member initializer list. So here, the DS member of the object C is being initialized with the string James here. That's also considered direct initialization. Now, one of the rules that C++ tries to abide by very carefully is that we want class types and built-in types to basically look the same. A lot of that comes from the ability to write class types that have overloaded operators, so we can make them look and feel very much like the built-in types that we're familiar with. But another way that shows up in C++ is that C++ extended direct initialization so that while you couldn't initialize an int or a double like this in C, you are allowed to in C++. Now, aggregates didn't initially support direct initialization. That wasn't added until C++20. I'll talk more about that a little later on. Back to this first example with the demoster direct initialization that I mentioned. That second one, DS2, is being constructed using demoster's copy constructor. Now, earlier I used the term copy initialization. And so, common point of confusion, it's easy to think, well, it's calling the copy constructor, that's gotta be copy initialization, right? But in fact, this is still performing direct initialization, even though it is invoking the copy constructor. Copy initialization happens, well, it happens in a few different situations, but perhaps most notably, it happens when we specify the initializer with an equals sign like this. So here, DS3 is being copy initialized, whereas DS2 is being direct initialized. And Moreover, although we're using the equals sign there, the initialization of ds3 there doesn't invoke the operator equals member function on the demo stir, even though it does have an overloaded operator equals function. This is down to the distinction in C++ between initialization and assignment. And it's easy to get these confused because they use the same symbols in some situations to mean what are effectively different things. That wasn't originally the intention if you read Design and Evolution, but it was how things worked out for efficiency reasons. So initialization gives an object its initial state. It's something that happens when an object is created. So regardless of whether the initializer is specified with an equal sign or in parentheses, that initialization invokes a constructor. It doesn't invoke an operator equals function. Operator equals gets invoked during assignment when we're overwriting the value of an object that already exists. So here in that bottom statement there, you can see that ds1 is not being created there. It must already exist because we're not specifying its type. So we can tell that that's a case of assigning to an existing object. And that's when the operator equals function would be invoked. Oh, by the way, if you have any questions, we have a mic up here in the front. I'm happy to take questions during the presentation. One of the effects of that is, one of the reasons why there's this distinction between initialization and assignment is that because assignment is overwriting an existing object, there might be existing state information that needs to be cleaned up during that assignment. Like there might be memory that was already allocated for the previous state of the object that needs to be deleted before the object takes on its new state. So I mentioned that copy initialization occurs when we use the equals sign. More generally, it occurs when the initializer is given with an equals sign, or when passing or returning an object by value, or throwing an exception or catching an exception by value. All of those are examples of copy initialization. Now, I say that one of the things that makes talking about initialization complicated is that when we're talking about initializing, say, a class object, something that has internal structure, I've mentioned that there are these different forms of initialization. Initializing an object of a class type might involve a different form of initialization from the way that the members of that type are initialized. So here, for example, this is an implementation of demo stir's copy constructor. And notice stored length and actual stir here. Their initializers are provided in parens in the member initializer list. So they are being direct initialized. And that's true regardless of how the demo stir constructor itself is invoked. This same constructor will be used to initialize both ds2 and ds3 down there, even though ds2 is being direct initialized and ds3 is being copy initialized. So we need to be careful when we're talking about initialization. When we need to distinguish between these things, we might need to talk about which initialization is part of a whole. Often we don't need to go to this level of specificity, but the compiler goes to this level of specificity. And so when we encounter errors, it can be important to speaking the compiler's language can help us fix those problems. As another example of a sort of mixed mode initialization, when we brace initialize an aggregate, each individual element behaves as being copy initialized. So here, W1 is being aggregate initialized, but the individual fields, those are copy initialized. Now, why do you care about the distinction between direct initialization versus copy initialization? One of the big reasons is it affects which conversions are allowed. So a constructor that does not have the keyword explicit on it is, or can be, what we call a converting constructor. That is, it can be used as the compiler may use it automatically to perform an implicit conversion from the types of the arguments to the constructor to the class type being constructed. Usually we think about this when there's a single argument to that constructor, but it can actually occur in modern C++, it can occur with constructors that take multiple arguments as well. So here, earlier I showed you demoster with having this constructor that takes a pointer to an array of characters, traditional C-style string. If I have that constructor, here I have another function f that takes a demoster by value. Pass by value uses copy initialization. So I can call the f function, passing in something that isn't really a demoster, at least not initially. What I'm passing in there is a string literal, an array of characters, but the compiler will use that constructor on demoster to convert that array of characters. Well, first it'll convert it into a pointer. The array will decay into a pointer, and then it will convert the pointer into a demoster object by calling that constructor. So it will behave, inside the function, we will see a demoster object that was created as the function was being called and is destroyed when the function returns. That is true as long as the constructor is declared like that. If I declare the constructor to be explicit, then this call is no longer valid because the constructor has been specified to be only used for explicit conversions. Copy initialization will no longer automatically invoke this is no longer considered a converting constructor. Copy initialization will no longer invoke it. It can be invoked through direct initialization, but the conversion won't happen implicitly as part of copying. Now, this is a situation where you might have said, well, why didn't you cover this part earlier? If we leave off the parentheses entirely, if we don't specify an initializer for the demoster, the default constructor will be called. We call this default initialization. Yes, there really are all these terms. I wish that there wasn't quite as much of a mouthful as there is, but they were created with good reason. So now, this is how objects with default constructors like demoster operate. As in C, objects of scalar type, objects with no initializers, are left uninitialized. Now, this leads to a little bit of confusing terminology here because C++, in some places, the standard says X is uninitialized, and in other places it says it's default initialized in the sense that its lifetime has begun. An initialization that does nothing is still considered initialization for the purposes of telling us when that thing officially becomes an int, essentially. So while it's easy to call this thing uninitialized, and I think it's correct to do that, what you'll see if you really look deep into the standard is that there's this technical term vacuous initialization for initialization that does nothing. And when they want to describe when an object's lifetime begins, that vacuous initialization is the term that gets used. Now, if I tried to include empty parens as the initializer here, I suspect that some of you have run into this problem before. This does not actually declare an object of type demoster. It declares a function that takes no arguments and returns an object of type demoster by value. This is essentially a consequence of the rules for parsing function declarations. There's this unfortunate ambiguity in the language. And this is really, in some ways, a special case of what Scott Myers called the most vexing parse error in C++, where if something can be read as a function declaration, the compiler will read it as a function declaration. So I think a lot of people, the first time they see code that looks like that, their intention there is probably to create a vector, v1, by calling a constructor passing in cin, an iStream iterator created out of cin, and another iStream iterator that specifies the end location of the input stream, essentially. But in fact, the compiler reads this where those iStream iterator pieces highlighted in red are treated as the parameter types in a function declaration. The parameter cin is treated as the parameter name, and the second parameter is treated as an unnamed parameter. And the parentheses are just ignored as being superfluous. You can throw in extra parentheses when declaring a name, and the compiler won't complain about that. It'll say, okay, they're a bit pointless, but looks like an ordinary function declaration to me from the compiler's perspective. And this is the kind of problem that can occur in C++, and one of the things that modern C++ was attempted to fix as time went on. Now, although we can't use empty parens as the initializer on a traditional object declaration like I showed earlier, we can use them as the initializer, say, in a member initializer list, or when we are dynamically allocating an object using new. And in this case, the parentheses actually do mean something specific. They perform a specific kind of initialization called value initialization, which is close to, but not quite the same thing as default initialization. Exactly what value initialization means depends on what kind of object, what kind of type T is. So if T is a class type with the user-provided default constructor, value initialization just calls it. If T is an array, value initializing an array means value initialize all of the elements. If we're talking about a simple scalar object, value initialization zero initializes it. So if the type was int empty parens being dynamically allocated with new, that int will have the value 0. Otherwise, the initialization is only valid if T has no user-provided constructors, and generally because T is an aggregate, in which case the behavior is go through the data members of the T object, 0 initialize them, and then default initialize them, because they might be, the members of T might be class types that have constructors. Now, we can value initialize objects that we're declaring on the stack, for example, but it's a little bit roundabout in CppCon. I have to write something that looks like this, where I specify the initializer, the value initialization on the right-hand side of copy initialization. So what I'm showing you here, this is really a combination of value initialization and copy initialization. It's something that we could do in C++03, but it was a little bit, wasn't necessarily the clearest thing to do. And up until C++17, if I were to write value initialization that way, it required an accessible copy constructor. If I tried to follow the C++03 mode of disabling the copy operations in a type like C here, then I would get an error message when I tried to do that kind of value initialization because the copy constructor would not be accessible. As of C++17, that's no longer an issue because we have mandated copy elision, as it's called. So what were some of the problems that the Standards Committee wanted to address in C++03 by introducing new forms of initialization? Well, there was no uniform initialization syntax, which was a problem for templates. We sometimes had issues with what we call narrowing conversions. The value initialization, as I told you, could be roundabout in some situations. And there's also an issue with initializing STL containers that I'll talk about in just a moment. So in C++03, we can think of it, I've mentioned these 3 different categories of objects that we can have: scalars, aggregates, class types with user-provided constructors. If you dig into the standard, you will see some others like references, but I've set those aside for the moment to focus on the places where I think the confusion is most significant. When we're talking about these 3 kinds of types, there's no form of initialization that works for all of them. Scalars and classes can't be brace initialized, whereas aggregates couldn't in C++03 be direct initialized. So in a template context, it was difficult to know whether a type was going to could be initialized in a particular way. When you wrote your templates, you had to make a decision about what kind of initialization you were using. There was also an issue, the language has a lot of conversions that are built in. And many of those conversions can involve a loss of information. In C++03, if you initialize an object in a way with an initializer where some information is being discarded as the object is being initialized, you don't get any protection against that. The compiler may very well just silently do something like convert the float into an int by discarding the fractional part, or convert an int into a short, and if the int doesn't fit in a short, tough, you get what you get. And that can be, and even things like converting an int into a float can be a narrowing conversion, because if int and float are the same size, float, the way that floating point values are represented, the float will be an approximation of some values that could be represented exactly as an integer. So that would also be considered a narrowing conversion. As I mentioned, initializing things using value initialization was difficult in C++ 03. And in particular, if you saw that third form, the thing that's a combination of value initialization and copy initialization, I don't think it's very self-explanatory. It's easy to look at that and think, oh, that was default initialization done by someone who was maybe used to another language like Java or something like that, where they meant, I can just remove that initializer, it'll mean the same thing, right? Often yes, but not necessarily. So, but it was easy to make that kind of mistake. And then I mentioned that initializing STL containers could be difficult. We had an easy way to initialize arrays with whatever contents we wanted to give them. But to initialize an STL container, like a vector, with whatever contents we wanted to give that vector, that was more difficult. I could do something like this, where I initialize the vector using iterators, but I really have to have another collection that already contains those values, which isn't really, that's kind of annoying. It's not helpful in a lot of situations. Certainly, it can be wasteful. And so these problems sort of became that much more serious in template contexts, because I could write something like this initialization of x from an object of type t. Is that a narrowing conversion? Is that safe to do with no loss of information? I don't know. Depends on what t is. In this case, I've declared an object of type t. It doesn't have an initializer. Does that mean it's uninitialized? Does that mean its default constructor ran? Wasn't a good way to know. If we wanted, we could use the value initialization approach, but that required that the type be copy constructible, which might not necessarily be true for t. And if we tried to use something like aggregate initialization, that's something that would only work if t was an aggregate. So we had to make these difficult choices about how to write our templates that in ways that would work for some types, but maybe not all of the types that we were hoping that our templates would work for. So modern C++ tried to address this by using brace initialization as a form of uniform initialization syntax, as it was called. And so all types now support initialization with braces. Notice none of those examples there have an equal sign. It's just braces by themselves. Works for scalars, works for aggregates, works for classes with constructors in general. Now, unfortunately, the intent was that this might be the one true way to initialize things, but in practice, there are still good reasons to use other forms of initialization in modern C++. But first, let's go through some of the positives, what we do get out of modern C++. So the empty braces now give us a convenient way to perform value initialization, and we don't have to worry about the ambiguity that something might be interpreted as a function. So here, whereas the declaration of y there is actually declaring a function that returns an int. The declaration of z is creating an object z that is 0 initialized. And this can be used in that context or in other contexts like a new expression. The empty braces there will perform value initialization. And this works both for simple types like integers, scalars, as well as class types. In the case of a class type like demoster, it will invoke the default constructor, assuming that the type has one. But so it'll be similar. The initialization of DS1 and DS3 will be very similar, but it makes life easier often when writing templates. So now I can write a template like this, and here using the empty braces, I know that obj is going to be initialized to something. If it's a class type with constructors, the default constructor will be called. If it's a scalar type, then the object will be 0 initialized. Now, I can use braces to, what I've been showing you so far here, the braces, I'm using them to perform a form of direct initialization. Yeah?
Sorry, I had a quick question about the last slide. So we know that T, or that obj, is definitely not uninitialized, but do we know that kind of recursively for its members? Like, is it possible that some members could be uninitialized depending on how the class T was defined?
Yes, in a rare circumstance where if T is a type for which I wrote my own constructor, and I deliberately didn't initialize a field. I specifically did not initialize something, and it does not have a default constructor that would take over. It would be left uninitialized according to the usual rules of initialization, like for a scalar. Yes, then in that situation, this thing would be, there might be fields that would be uninitialized. But if this is a class type for which the constructor, the default constructor is being generated by the compiler, then it would recursively value initialize all of the members of the type going down. Yeah, good question. Yes. So the form of list of brace initialization that I've been showing you so far is what we call direct list initialization, very similar to direct initialization, although there are a couple of differences that I will talk about in a moment. But based on what I've shown you so far with the definition of the demoster class that I showed you earlier, in this case, both parentheses and braces will result in the same constructors being invoked here. And again, direct list initialization can be used in the same kinds of places where we use direct initialization, such as in the member initializer list in a constructor. If I combine the brace initialization with an equal sign, now I get what we call copy list initialization, which again is similar to copy initialization with some slight differences. So here, these are all forms of copy initialization. Some of the ones that use braces are performing copy list initialization, but the same constructor for demoster is being invoked in both cases. And as before, this difference between direct list initialization and copy list initialization mainly comes down to whether explicit constructors are considered. So if demoster's constructor that took a C-style string was declared explicit, then direct list initialization, like we're seeing for the object C1 here would be permitted, but the copy list initialization that uses the equals sign, in that situation, that would be flagged as an error because it involves an implicit conversion from C-style string to demo str. And in copy initialization contexts, that kind of conversion that we've marked, a constructor that we've marked explicit there would not be invoked. Okay. So, I mentioned that there are a few differences that brace initialization gives us. One of them is that it prohibits narrowing conversions in general. So if I were to try to initialize an int object using traditional copy initialization with a value that doesn't fit in an integer, like 12.3, that would work in traditional, that would work with the traditional forms of initialization, but brace initialization would flag it as an error because that would be a loss of information. The same thing occurs if I'm converting an object of a type like int to a smaller type like char, or to a potentially less precise type like float here. These statements would be flagged as performing narrowing conversions. Now, if the initializers are constant expressions where the compiler can look at them, the compiler may be able to verify that in this case, for example, 12 will fit in a character, or that 12 can be exactly represented as a float, then it will permit those conversions. The compiler is smart enough to only complain when there actually will be a loss of information, if it can tell that that will be the case. If you're dealing with something that's not a constant expression like I here, then the compiler has no choice but to assume that it's a narrowing conversion. Now, there are times when we might need to use narrowing conversions. They are important in some software sometimes. So if we are using brace initialization, we could use the traditional form of initialization, or to show that we intentionally want the narrowing conversion, we know that that's happening here, we could choose to use brace initialization and an explicit cast. Generally speaking, casts are something that we want to be very cautious about. We don't want to use them if we don't have to. But if the conversion is going to occur, it's probably better to explicitly mark it as occurring rather than having it occur silently. So, although narrowing conversions would be allowed on assignments, we don't have an equivalent of brace initialization for brace assignment, you might want to, in that situation, also use an explicit cast, again, to convey intentionality in this kind of situation. One of the problems I mentioned was the ability to create a type, like an STL container with arbitrary contents. We can now write types that can be constructed with lists of values, and we do so by writing a constructor that takes an argument of type std initializer list. So here is a new version of the demo str class to which I've added a constructor that takes a std initializer list of characters. Initializer lists are often passed by value because they involve a shallow copy, so that would not be a particularly expensive thing to call from that perspective. So a constructor that takes a std initializer list, I could invoke that in one of these ways, either through direct list initialization or copy list initialization. Sorry about the sound. And there's actually nothing special about list initialization here. If I go ahead and create an object of type initializer list, of an initializer list type, then I could use the other forms of initialization as well. The compiler won't assume that, but there's nothing magical about brace initialization that needs to work with std initializer list, even though that is the way that things are generally intended to be used. It's meant to be convenient. It's not meant to be mandatory. Now, if a type has both a default constructor and an initializer list constructor, then the empty braces will invoke the default constructor. If there's just an initializer list constructor and no default constructor, the empty braces will be interpreted as an empty initializer list. Now, I encourage you not to write types where the distinction between where an empty list will initialize something differently from the way that a default constructor would, but you are technically allowed to write that. I just think I think the number of situations where an empty list should result in something different from just build me one by default, pretty slim. All right, so the initializer list type supports iterators, much like the STL container type. So in some ways, it can be treated like an STL container type. So here is a possible implementation of demostir's initializer list constructor. I'm getting the size of the list, that's my stored length, allocating the array as before, and then using the standard copy algorithm to fill in the array allocated for actual stir, and then null terminate it at the end. Now, often, when we're dealing with a type that has an initializer list constructor, it's often a class template, something like the vector type in the standard library. So here, this is a simplified picture of what vector looks like. The real type definition is substantially more complicated than this, but this is just meant to give you some idea of what you might see if you looked inside a vector. You'd see an initializer list constructor of t's, and that lets us create a vector of, say, integers with a brace enclosed list of integers. Now, this is where some confusion can really creep in, because if we're talking about a class type that has an initializer list constructor, that's where it really becomes a concern that parenthesis initialization, direct initialization versus direct list initialization, or copy initialization versus copy list initialization might invoke different constructors. And that's particularly true when we're talking about templates, because when we're dealing with a template, the user could create a template where the parameter types match the types of other constructors that we chose to write for that class template. So I think these declarations, these definitions all invoke the constructors that you would expect. A is default constructed. B uses the one argument constructor that I showed earlier. C uses the two argument constructor that I showed earlier. So those first two constructors listed there. And then the final example there for D is using the initializer list constructor. That, I think, is not too surprising, but what is a little surprising for some people is that a brace enclosed list where the values could be interpreted as arguments to the other constructors, overload resolution favors the initializer list, as long as the values in the list can all be interpreted as an initializer list of the same type. So The root of the problem here being that vector has a constructor that takes a size type, which is an unsigned type, but integers can convert into unsigned values. Or it has a constructor that takes an initializer list, and if we're talking about a vector of ints, the compiler is forced to choose, and in the case of brace initialization, it will choose the initializer list constructor. So one of the consequences here is when you're creating a new type, you should think carefully about whether or not it should have an initializer list constructor, because including one could lead your users to experience the same kind of confusion that we just saw. The standard library types are usually a pretty good model for designing these things, but the standard library was sort of in a special position when they were adding these initializer lists to constructors to the STL types. What you really don't want to do is add or remove a std initializer list constructor from an existing type, because if you do that, it can silently change the meaning of existing code. So here I have a type C that does not have an initializer list constructor, and the definition of C1 down there calls the constructor that I've labeled number 2, the one that takes exactly 2 integers. But if I add an initializer list of int constructor to that type C, the meaning of that definition for C1 silently changes. That's a typo there. That should say it used to call 2. And this is one version of the problem, but the same problem can occur in the other direction if you remove a std initializer list constructor. Now, as I said, the standard library was in a bit of a unique position because the authors of the standard library knew that no one was writing code like that. There couldn't be brace initialization code for a vector out in the wild at the time that C++11 was released. So there wasn't the potential that the meaning of code was silently changing, but I think it's a fair assumption that usually your types are likely to change more often than the standard library types do. A lot of types we have to maintain much more rigorously than that. Now, this is mainly a concern if we're talking about, this is mainly a concern when the brace enclosed elements can all be interpreted as the same type. Here, the compiler has no difficulty figuring out that the definition of DS there is using the first constructor because hello world and 5 can't be interpreted as the same type. They wouldn't both be characters or ints or something like that. So there, it's clear that to the compiler that what we meant was the constructor labeled number 1 there. Now, because although brace initialization was intended as this uniform initialization syntax, this potential for confusion means that it's not necessarily the way that we want to initialize things in templates. So here, I'm creating a unique pointer to a vector. Which constructor of the vector does that call to make unique invoke? Does that create a vector with 12 negative 1s in it? Or a vector with a 12 and a negative 1 in it? It depends on whether make unique is written like this to use direct initialization or something more like this using parenthesis initialization. These are oversimplified versions of make unique, but just to illustrate the point. Now, the rule in the standard library is that make unique and similar functions use direct initialization. So this would create a vector containing 12 copies of -1. Part of the reason that they did that was because if you want to use the initializer list constructor, you have the option of manually creating an initializer list and passing that in as the argument to make unique. So I think if there's any doubt, you want to follow that model set by the standard library. People are generally familiar with the standard library functions. If you have a good reason to use something different, I think you want to clearly document that in your interface. But what about aggregate initialization? Because originally, make unique wouldn't be able to initialize an aggregate like S here. But fortunately now, C++20 allows for direct initialization of aggregates with parentheses. So we're now in a much better position to use make unique in general. So what I'm hoping you'll take away from this, the initialization rules evolved the way that they did to avoid breaking existing code. You want to try to do what you can to keep the different forms of initialization clear. And you want to decide up front whether types should have a std initializer list constructor or not. Okay, that brings me to the end. Thank you very much for coming. Enjoy the rest of CppCon 2023.